In this lecture, we're going to go over how to make trend lines in MATLAB. So we're going to learn how to display trend lines using the polyfit function for linear power or exponential trends. We're going to place the trend line equations on our graphs, and we're going to use polyfit to determine the mathematical fits to our experimental data. And we're going to use models to predict behavior of the system under study. So how do we graph a trend line in MATLAB? So what we do is we create a proper plot of the data points only. We determine the form of the relationship of its linear power or exponential. We use the appropriate polyfit command based on step 2 to determine the parameters m and b for the trend line equation. We then create a theoretical data set for which the trend line will be plotted. We set up a sequence of values for the independent variable, or our x-axis. The range of these values should normally be similar to the range of the experimental values. Then, using the sequence and the values of m and b determined in step 3, we calculate the corresponding values of our dependent variable on the y-axis. For example, if x goes from 1 to 10 in steps of 1, y is equal to mx plus b. We add the theoretical data set of x and y to the graph created in step 1. We add the proper plot elements such as a trend line equation to complete our graph. So this is what a proper plot looks like with data and a trend line on it. Notice we have our trend line and our equation for our trend line. So how does the polyfit function work? The polyfit function accepts two equal-sized vectors containing the data to be modeled. The first vector is the independent variable. The second vector is the dependent variable. It finds a polynomial of the order n that best fits the data. So it's polyfit x, y, n. The C vector of results has C of 1 as the highest power coefficient. So the x is the x vector, the y is the y vector, n is the order of the polynomial. So for linear relationships, what would we do? So in this example, I have some springs, we have some more initial data, we have our extension, our mass, and we have weight is equals mass times gravity. We're trying to find a polyfit between our extension and our weight. And 1 is because it's a linear relationship. We are always using 1 in this course. So the spring coefficient, the spring constant is going to be the coefficient of 1 because it's the highest order first, so it's mx plus b. So first we'll give our m, and then our initial weight would be our coefficient of 2 in position 2 because our coefficient would be our b, and that is the second thing that we would find. Then we can calculate our extension, use our spring constant, and calculate our mass. So for a linear relationship, what do we have? We have, to find our polyfit, we have C is equal to polyfit x, y, 1, where our variable C will contain m and then b. So m is C of 1 and b is C of 2. In this example, we're plotting distance versus time. So I have my time vector, I have my distance vector. I plotted distance versus time. I made it red diamonds. I put in my marker size of 10, my face color of 111, which is white. We know it is linear, so we're going to determine our polyfit. So my polyfit of my time, my distance 1, my slope is C of 1, my intercept is C of 2. I'm going to create some theoretical data, so I'm going to say T2 goes from 0 to 120 in steps of 5, and my distance 2 is m times T2 plus b. Then I'm going to graph it. To graph it, I must employ the hold on function to put more than one line on the same plot, otherwise it would erase all of my previously existing data. Then I'm going to plot my T2, my D2, R, I'm going to make it a red line with a width 2. Then I'm going to create a variable TE. I'm going to say S print F. D is equal to 0% F, T plus 0% F with M comma B. This is creating my equation. D is equal to 5T plus 2. That's one of the main uses of the S print F command from before. So this text 35,450 TE is putting this in coordinates. It's over 35 up 450. Right, so here's 35, 450, that's where it's putting the text box. I'm adding some axes, titles, labels, and putting my grid on. So what do hold on and text do? Let's look at these closer. So recall that we mentioned earlier that plotting commands such as plot erase whatever is currently in the most recently used figure window, and then draws a new graph. So to prevent erasing of the data points that we plotted earlier, we have to use the hold on function. before drawing our trend line. Hold on tells MATLAB, do not erase the current figure window, but merely add new information to what is already there. So to add the expression on your graph for our trend line, you need to provide coordinates where the equation should be shown using the text function. The values for x and y, the values for the x and y coordinate use the actual coordinate values on your axes. So the left center end of the text string will be located at these coordinates. To form the text string function, use the text function, which is text, x coordinate, y coordinate, text string. So that's how it works for linear relationships. Let's look how it works for power relationships. So MATLAB does not have functions built in to directly calculate the parameters for power and exponential models. You can't just click a button like you could in Excel and get a power model or an exponential model. So if we recall that our power model is y is equal to b to the mx, and if we take the log of each side, we have the log of y is equal to log of b plus m log of x. That is our linear form. We can use polyfit to create a linear fit between log x and log y to calculate the value of m and log of b. We have to raise 10 to the second coefficient return to get the actual value of b. Note that this is that log base 10 in MATLAB is log 10, not just log. So c, in our case, c would be equal to polyfit log 10 of x log 10 of y comma 1. Our slope would be c of 1, and our b would be 10 to c of 2. So here we have our summary of power relationship. Or again, it's polyfit log 10 of x log 10 of y comma 1. And then c contains m, the log 10 of b, so m is equal to c of 1, and b is 10 to the c of 2. So let's look at an example of this. So here I'm plotting distance versus time. We have it's going to be distance versus time. It should be current and power. I forgot to update the axes. So we're going to graph our experimental data. So we're plotting I comma p. We're going to make it blue squares, setting our marker size and our line width of those squares. Since we know it's a power relationship, we're going to determine the parameters using our polyfit. So we have polyfit log 10 of I, log 10 of p. M is c of 1, b is 10 to c of 2. Then we're going to create our theoretical data. So we have I2 is equal to 0.5 to 3.5 in steps of 0.1. P2 is equal to b times I2 to the m. We're going to use our hold on function to be able to graph the second line, which is our second plot, I2 comma b. P2, we're going to make it a blue solid line with a width of 2. Again, we're going to make our text string, which we're going to use our sprintf command for. Then we're going to place that at 0.955. So if we come over here, we're at 0.9 and 55 is where the center left of this equation is being put. Also using the font size command in there to set it to be a font size of 20. We formatted our axes, our titles, our X labels, our Y labels, and we used some more formatting to set their sizes. So what about an exponential relationship? Again, we don't have an equation that's going to do it for us. We have to get a linear form. So we're going to take the natural log of it for this case. You could do it like we did previously. It's just a little bit easier if we do it with the natural log since our slope comes out and we don't have to divide. This is different from what we were doing previously when we were looking at graphs because we were looking at a log-log graph. It's essentially a linear model, so we can use polyfit to create a fit between x and the natural log of y, and again to calculate the values of the values of m and the natural log of b. The natural log function in MATLAB is the log function. So to get the actual value of b, again, we need to raise e to the value that we've gotten. So it would be c is equal to polyfit of x comma log of y comma 1. M is c of 1, and b is an exponential of c of 2. So let's look at an example here. We're trying to plot concentration versus time. We're using magenta asterisk with a marker size of 10 and a line width of 1.5. We're using our polyfit of our time and our log of our concentration to get our slope and our b, which is the exponential to the set what was returned because we're doing a polyfit on a linear graph of our manipulated data. We create our theoretical data. We use our hold on function to plot a second line on our graph. We plot our second line. We create a texturing variable to store our equation. We then put that texturing somewhere on the graph that we like. We make our axes limits. We put on our title, our labels, our ticks, and we format our x-axis font size to be 14. So a note on figure text, superscripts and subscripts do not work correctly when placing text on a figure. For example, if you try typing place x to the 4.25 on a plot, it's going to generate x to the 4th because, again, our caret superscript says to make the next single item a superscript or a subscript. So the solution is to put the exponent within curly brackets because it turns that into a cell array, which then essentially makes it the next single entry. For example, if we want to place H sub FE in the plot title, the solution is to write title H underscore FE in curly brackets. It's the same as we use for superscripts, but using the underscore character to make a subscript. So let's look at the code that we would need to create this graph. We're trying to create a graph that has a trend line on it, that has a red background, black text, blue diamonds, and a dotted blue line. So first thing we do is we create our figure with our white background. We have our initial data. We're plotting all of the rows in column 1 versus all of the rows in column 2. We're making them blue squares. We're giving them a marker size of 14 and a face color that's blue. We're then using our polyfit function. We're going to do the log of each since it is a power fit. Our slope is c of 1. Our b is 10 to the c of 2. We're going to make our theoretical equation with f. We're going to use our hold on function to put our second plot line on there. We're going to create a text string of our equation. We're going to place that text string on our graph with a certain font size and our background color. We're going to format our axes to have limits of 0 and 40 and 0 to 15. We're going to make our title to say swing things. We're going to give it a font size of 20. We're going to make it italic. We're going to also make it blue. We're going to give it labels. We're going to give it axes ticks. And this last bit at the bottom, I'm saying AX is GCA. GCA is graphical formatting, and I'm going to say the dot for axes. These are using some structures arrays that we didn't really cover. And that is it for graphing in MATLAB. What we're going to do next is look at statistics. We'll learn about statistics, then we'll do statistics in Excel, and then statistics in MATLAB.